Hello, everyone. Today we're happy to be welcoming Professor Mordo Shalom. He will be talking about the complexity of various reload/changeover cost problems. And he has fascinating research on graph theory. Let me tell you very briefly about his bio. He received his PhD in computer science from Technion in 2006. And since then, he's been serving as a senior lecturer in the Tel Hai Academic College and as an adjunct lecturer at the Technion. His research interests are optimization problems in optical networks, distributed algorithms, approximation algorithms, online algorithms, and algorithmic graph theory. Incidentally, interestingly, he holds a bachelor's degree in architecture from the Technical University of Istanbul. And he's worked in various alongside academia, he's contributed to industry as well. Hopefully we'll be seeing him in Istanbul soon. He's at the moment visiting, but he will be permanently teaching in Istanbul soon. And with that, with that, I'll leave the floor to Professor Shalom.
Thank you very much, Elifoja, for the introduction. Let me share my screen first. Okay, yes, perfect. Okay, so I will talk about multicast communications with varying bandwidth constraints. I will define the problem soon, but the main important word here is varying. So this is a joint work with Yuval Emek, Shay, Kutten, and Shmuel Zaks, all from the Technion. And the motivation is the following problem. You have a communication network of tree topology, and you have multicast communication requests, which are subtrees of the big tree T. And every such communication request has some demand. And the goal is to maximize the number of requests, such communication requests, to satisfy simultaneously, of course, subject to the capacity constraints of the network. So it's a very natural network scheduling problem. So this is the formal definition of the problem. You have a tree T, you have a multiset calligraphic T of subtrees of T. For every node of T, you have an integer, and for every vertex, for every edge, this is an error, of T, you have another number. So you have integers all over the tree, and you have to find a subset of these subtrees calligraphic T of maximum cardinality, of maximum number, such that at every node and at every edge, the capacity of this edge or node is not exceeded by the subtrees S. So this is the definition of the problem. Now, this talk is maybe more on related problems and related algorithms than our problem and our result. So it turns out that this problem generalizes other problems in literature, and also our solution generalizes the same solution. So it's so I will talk first of all about graph coloring. If some of you don't know what's graph coloring. So graph coloring is the task of assigning colors, which are numbers, frequencies, or wavelengths, to vertices of a given graph, so that no pair of adjacent vertices get the same color. For instance, if you have communication entities, you don't want to assign the same frequency to nearby transmitting stations. Okay, so you don't want two adjacent vertices to get the same color. So color can be anything. And the goal is when we say graph coloring, we mean implicitly that the goal is to use the smallest number of colors possible. And this number is called in graph theory the chromatic number of a graph. So there is some number that you cannot color the given graph below that number. So this is called the chromatic number of the graph. Let's make a small example. So this is not a proper coloring of this graph. So we have the graph consisting of 5 vertices, the cycle, the 5 cycle. This is not a proper coloring because you have 2 vertices. For instance, these 2 vertices are adjacent and colored with the same color. And similarly, this coloring is also not a proper coloring because you have these 2 colored with the same color, these 2 colored with the same color. But this one is a proper coloring. No 2 adjacent vertices receive the same color, and you have now 3 colors. And you can easily prove that this is the smallest number of colors possible. Every odd cycle can be colored with 3 colors, and you cannot do less. So this is about graph coloring. So I mentioned that we will have related problems. So I will mention 2 related problems. One of them is a coloring problem, the maximum k-colorable subset problem. So you have a graph G, a positive integer k, and the goal is to find a k-colorable subset S of the vertices of G. So G may be k-colorable or not, but you want to find a subset S such that only this subset can be colorable with k colors. And of course, you want to find a maximum number, a set that has a maximum number of vertices. This corresponds, for instance, if this is a communication graph, you want to find, you have k frequencies, and you would like to assign these k frequencies to a subset S of the vertices such that no 2 vertices in S assigned the same color interfere with each other. So you want to find the biggest set that you can allow to communicate within the given k wavelengths or frequencies. So this is the maximum k-colorable set problem. You want to find the biggest set. Now let's go. So this is about coloring. Another concept that I want to introduce is chordal graph. What is a chordal graph? A chordal graph, of course, is a graph that does not contain chords. Yes, that does not contain chords. Let's say in another way, it's a graph that does not contain holes. Okay. So what is a hole? In the gray graph, this is a hole. A hole is a cycle that does not contain, so consider this cycle, 5 cycle without the green edges. This is a hole. This is called a hole. A hole is a cycle with at least 4 vertices. So this is a hole, and this graph is not chordal. But if you add these 2 green edges, now you have 3 cycles, none of which is a hole, and this graph is now chordal. A chordal graph is a graph that does not contain holes. So what this problem what these graphs have to do with our problem? Now the point is that there is a very interesting characterization of these graphs as follows. Every chordal graph corresponds to a set of subtrees of a tree, and vice versa. Every set of subtrees of a tree correspond to a chordal graph as follows. So this is a graph, this is a chordal graph. You can check that there are no holes. And this is the subtree representation. What does it mean? For every vertex, for instance, B, for every vertex of this graph, let's take this vertex B, there is a subtree. In this case, it's a pet. So this example is not perfect in the sense that all the subtrees here are pets, but it could be also some other subtree. So, for instance, B is adjacent to A. And here the subtree A is a subtree consisting of this vertex only. and B is the red subtree, and they intersect in this node. So therefore, since A and B, the subtrees A and B intersect, there is an edge between A and B in the chordal graph. So we say that this chordal graph is a vertex intersection graph of these subtrees of the given tree. Again, it could be the case that, for instance, if I extend this, this 3B, red 3B, in this way, then B becomes adjacent to C, E, and D. B is already adjacent to C, C and E, so it becomes adjacent to D. Then you have, in addition, this edge. Now this representation is the subtree representation of this graph. Okay, so this makes the connection between our problem and chordal graphs. So another, clear. Okay, perfect. Yes. Now, there is a trivial lower bound about coloring. You cannot color the click number of a graph is a lower bound to the chromatic number. Why? For instance, take this graph. Here, if you take these vertices, these green vertices, they constitute a click because every pair of them is connected to each other. So this, you see, Y is connected to tilde X and tilde X is. So you see here a triangle, every pair is connected to each other. Therefore, you need at least 3 colors to color these 3 vertices. Therefore, you cannot color this graph with less than 3 vertices. And in this case, you actually can color this graph using 3 vertices because you can color them with color number 1, this color number 2, and this color number 3. And you can easily see that no vertices, the vertices of color 1 are not connected to each other, the vertices of color 2 are not connected to each other, and the vertices of color 3 are not connected to each other. So here we have an example that this bound is tight. However, you have already seen an example in which this bound is not tight. For instance, here you need at least 3 colors, but you don't have triangles. And so the click number of this graph is 2, but you cannot color it with 2 colors. So what's interesting for us is that the click number is a lower bound, so for the chromatic number. And actually, in chordal graphs, it is well known that the click number is equal to the chromatic number. Okay, so every node of T, when you look at this representation, every node of T corresponds to a click. For instance, you have B, C, E in the same node. Therefore, all these subtrees intersect at least at each node, at this node. Therefore, BCE is a click, and I see that BCE indeed is a triangle. So every node corresponds to a click, but it's also known the opposite, that every maximal click corresponds to a node. So this is less trivial to see, but this is well known. And therefore, we conclude the following. If I want to solve the maximum k-colorable set problem in chordal graphs, is equivalent to find a maximum subset of trees of a tree, such that at each node there are at most k subtrees. Sorry. Okay. For every node T, there are at most k subtrees of S that contain T, which means that this is a special case of our problem that we call it maximum subtrees with bounded load, with homogeneous capacity constraint. In our problem, you can assign to every edge and every node of the tree a different number, a different capacity. In this problem, in this special case, you assign the same number to all of them, and then this becomes the equivalent to the maximum k-colorable subset problem in Chordal Graphs. So this is one problem that related to our problem. Another problem is the maximum multi-commodity flow problem in trees. So what is a multi-commodity flow? It's like a flow in which you have a graph G, okay? You have commodities 1, 2, 3, etc. And now every commodity I has to flow from vertex Si to vertex Ti. Okay, so it's many commodities flowing is like many flow problems combined. And you want to find a maximum flow in this sense. And when your network is a tree, and of course edges have capacities like in ordinary flow problems, and you want to maximize the total flow. Now, when our tree, when the graph G is a tree, so we recall that there is a unique path for any vertex Ci to any vertex Ti, there is a unique path in the tree. So the flow requests are actually paths. So you have a tree and you have paths of the tree, which are a special case of subtrees. Okay? A path is a special subtree. And this is quite obvious that now this problem is exactly our problem when the subtrees are restricted to be paths. Okay, so this is easier to see. So we have the following thing. Again, we have our problem in which you have to schedule a multicast requests, which are subtrees, and you have varying capacities on the nodes and edges. If you restrict the capacities to be uniform, to be homogeneous, then you get the maximum k-colorable set problem. On the other hand, if you restrict the paths, the subtrees to be paths, then you get the maximum multi-commodity flow in tree networks. And the maximum k-colorable set problem in Chordal Graphs is known to be NP-complete, but both problems are known to be NP-complete. Therefore, of course, our problem is NP-complete because it generalizes both of them. And there is a 1.58 etc. approximation by 1 and Liu from 98, and the 2 approximation by Chakrabarty and Roy 10 years later almost. However, this will be interesting for our purposes, although invented 10 years later and giving worse performance. Now, as for the other problem, there is a 2 approximation for this problem, and Garg, Vazirani, and Yannakakis also introduce a polynomial-time solvable spatial case. So there is a special instance for which the problem can be solved in polynomial time. So this is what was known for these 2 problems. So what are our results? First of all, we show that this problem is much harder to approximate. You cannot get a constant approximation in most of the cases. And we also give a greedy algorithm, which is an M-approximation. What is M? M is the number of leaves of the subtrees. So you can get an approximation algorithm for this case. And when your subtrees are paths, like in the maximum multi-commodity flow problem, a path has 2 leaves, therefore you get a 2 approximation algorithm. So immediately our algorithm becomes a 2 approximation is implied by our algorithm. And also it implies a polynomial time algorithm for some other graph classes anyway. And also we extend the polynomial time solvable spatial case to a more general case, but I will not be talking about that result in this talk. So what is about, what is the hardest, what are the hardest results? The problem is hard to approximate within n to the 1 minus epsilon for every positive epsilon, even when the t is a star. So even the case of a star is very hard to approximate. But if you restrict n to 3, which means the number of leaves of every subtree is 3, then the problem is APX hard, which means there is a constant approximation, but no better than this. Again, I will not go into the details of what means better than a constant approximation. And the proof is by deduction from the independent set problem. So if you take any graph, so this is a graph, you can transform it to a set of subtrees of a tree. So you have here in this graph 4 edges. Therefore, you have a star of 4, this red star of 4 edges. And then every vertex, let's take, for instance, V. V is incident to E2, E3, and E4. Therefore, the subtree V is this subtree, E2, E3, E4. Okay, so you can represent every graph as a set of subtrees of a tree, and specifically, this will be a star. And therefore, if you assign k equals 1 to every object here, to every node and every vertex of this tree, to find a maximum 1 colorable set of this instance is actually to find an independent set here. Okay, and therefore this is a simple reduction from the general, from the independent set problem in general graphs to our problem. Therefore, all the results that I mentioned before are implied by the hardness of approximation of the independent set problem. This is about the problems. Now, I said also that the algorithm is the extension of known algorithms. So let's see the algorithms. The first algorithm that I want to mention is a very simple algorithm that I think everybody should know: earliest deadline first. So you have a timeline, you have jobs that, for instance, this is a job that should start at this time and end at this time. So these are your jobs, and you want to assign this job to one machine. You have one machine, and you want to assign them, to assign a biggest number of jobs that you can assign to this machine. Okay, so this is the maximum independent set problem in interval graphs. But so what is the algorithm? Earliest deadline first. So we go from left to right, and we find the first deadline, and we take this job into the result. We decide that this job will be scheduled to the machine, and if this job is scheduled to the machine, the other one cannot be scheduled. So we take this to the solution and we throw the other. And then we find the next job, the next deadline. We take this job to the solution and we discard the other two because you cannot take all of them. And we do this. Once again, we take this one, we remove the others, we take this one, we remove the others, and we are done. This is the earliest deadline first algorithm, and it's very easy to prove that this solution is optimal. So we go from left to right, and we take anything that can be added to the solution, we add it to the solution. This is a greedy algorithm. Now, I was unable to find one when this algorithm was discovered. So it's at least, I think, more than 60 years, but I don't know the exact number. Now, another algorithm, which is extension of this algorithm, is by Gavrili. published in 72, to find the maximum stable set or maximum independent set in chordal graphs. Now, instead of interval graphs, instead of having one interval, now you have one line. Now you have a tree, you have subtrees of a tree. We know that chordal graphs are subtrees of a tree. And you have the same problem. You want to find, now you want to find a set of subtrees that do not intersect each other. The biggest set of subtrees that do not intersect each other. And again, you have this greedy algorithm by Gabriel. You do a post-order traversal of the tree. You go in a bottom-up way. At every vertex that you stop, you process all the subtrees that are rooted at the current node. You go bottom-up, and at every vertex, you look only at the subtrees rooted at this node. And whatever subtree, whichever subtree you can add to the solution, you add it if possible. What if possible means? If possible means that if it does not intersect any other subtree taken so far. Okay, so this is actually the same algorithm if you think. If you have a path, you go from left to right. If you have a tree, you go bottom up. It's the same thing. It's a special case. The first one was the special case of this one. Now, again, Gabriel and Yannakakis at 87 extended this algorithm for internal graph, now this time to find the k-colorable set, maximum k-colorable set in interval graphs. Again, the same algorithm. You process the intervals in the EDF order from left to right, and you add the current job, if you want, to the solution if possible. What if possible means? If possible means if still can be k-colored. Okay, if you can color, if you can add this to the solution and the solution is still k-colorable, take it. So this is almost the same algorithm, but now the meaning of the word, if possible, changed. Now, another algorithm, pass one of algorithm Chakravarti and Roy, they solve the maximum k-colorable set in chordal graphs. Now, again, they do a post-order traversal of the tree. They process all the subtrees at every node. They process all the subtrees rooted at the current node. And again, they add the current subtree to the solution if possible. What does it, if possible, mean? If possible means if you can still color using k-colors. So only the meaning of if possible changes, but the algorithm is still the same. Finally, we have the maximum multi-commodity flow problem in trees. They do exactly the same thing. They process the tree in the bottom-up way. At every node, they look at the subtrees. In their case, the subtrees are pets. They add it to the solution if possible. Okay. The same algorithm all the time. And if you take this algorithm, you go to the special cases, you obtain the same algorithm in the same run. So you have this, yes, this relationship between the algorithms. Actually,
Shalom. Can I ask something at this point?
Of course, of course.
Previous slide, please.
Of course.
This is because of my ignorance of these definitions. So every tree is an interval graph automatically?
No, an interval graph is if the big tree is a path. Of course, the subtrees are paths, and then it becomes an interval graph. Now, in their case, you have a tree, but the subtrees are paths. A very good question, of course.
But how about a chordal? So a chordal graph then is definitely not. So a chordal graph cannot be a tree.
No, a tree is a chordal graph in particular. A tree is a chordal graph.
A tree is a chordal graph.
Yeah, I mean, it's important to emphasize that the chordal graph and its representation are different things. The subtree represents the chordal graph. So it's the representation. Okay. Yes. Now I am talking about the representation. All the time.
I was thinking literal tree.
No. The graph, yes, the graph, these trees and the subtrees are a representation of the Chordal graph.
I see. Now it's
Yeah.
makes more sense. Thank you.
Yes. So when they process the tree, I'm always talking in terms of the representation.
Mm-hmm.
Most of the talk is terms in terms of the representation. So you have a tree, you process them bottom up, you process the vertices bottom up. At each time you consider the current vertex, all the subtrees that are rooted at the current node, and you add, if possible, to the solution. And then you get this. This EDF is for interval graphs, when the entire tree is a graph and k equals 1. This is for chordal graphs, but k equals 1. This is for interval graphs, but for any k. When you restrict to k equals 1, you get this. This is for any k and chordal graphs, but still homogeneous. All the k's are the same. And now you have the heterogeneous case, which is the multi-commodity flow algorithm, but it deals with pets, with a tree, but the subtrees are pets only. So you have this situation, and now you have our algorithm that it is the same algorithm, but it handles also the heterogeneous capacity case. So the if possible means if at any vertex you will not violate the capacity constraints. And this is still implementable in polynomial time. And of course, the tricky part of this result is to prove that indeed this is an M-approximation. If you bound the number of leaves of a tree, you get to a number M, you get an M-approximation. But again, this is exactly the same algorithm. This is taken from our paper. Yes, we do some post-order traversal on the tree T. For every vertex V in this traversal, we consider every subtree T such that the root of T is equal to V. And if the current solution plus Ti will be feasible, then add it to the solution. Exactly the same algorithm in this sense. Of course, the if feasible will be different, but still polynomial time solvable. And we show that this is an M-approximation. Of course, there are a few open problems that are closely related to this problem. The weighted case. What is the weighted case? In which you don't want a maximum cardinality subset, you want a maximum weight subset. When you schedule a communication request or a job, you have a benefit that you obtained from scheduling this request, and therefore two communication requests are usually not equal to the other. So sometimes you prefer to schedule some other job. You want to maximize your benefit. So this is the weighted case. It might be more interesting. It should be more interesting. And another open question is that does maximum k-colorable set in chordal graphs admit a p-task? So a p-task is a polynomial time approximation scheme, is something better than a constant approximation, but if you are not aware of this definition, it's not worthy to enter it. And that's all. Thank you for attending.
Thank you so much. Any questions? Very nice font on the slide, by the way.